today going to be building off what we talked about on Thursday, which is multivariate autoregressive state space models, and how we expand those models to add in covariates, and why we would want to do that. All right, so why would we include covariates in our model? And that might seem kind of obvious. However, there are a lot of reasons that we include covariates that might not seem so obvious. So a really common reason we're using covariates is that we are trying to estimate the effect of that covariate. Do that all the time. Any basic multivariate regression class, you're going to be doing that. So that would be kind of the point number 2 there, is you're trying to understand the causes of variation in your data and whether the covariate of interest explains that variation. Another reason that we might include covariates in a model is that we intend to use those to make a forecast. So we think that these covariates explain the variation, and that's going to help us make a better forecast of what's going to happen in the future. But there's a couple other reasons that that we commonly include covariates in these multivariate state space models. And one of the big ones is that it can help us deal with problematic observation errors. So structure in your observation errors, so like they're temporally correlated, they're correlated across sites, that can be really numerically difficult to deal with and can really make it difficult to suss out that hidden process that you're trying to get at by using a state space model. So remember, we're using a state space model when there's some hidden process that we'd like to know about, but we have our observations that are observing that with some error. So we've divided our model up into 2 parts. And if those observation errors have a lot of structure, temporal correlation, say, that can make it really hard to get at that underlying process. So covariates can help us deal with that. So that might be why you're including them. Another reason, and I'm after this lecture, I'll try to code up an example to show you. It can be a really clever way to understand how a system is changing. And what I want to code up is an example of how you can use covariates to study changing seasonality in your system. All right. When we go to the breakout sessions, you're going to play around with an example using the Lake Washington plankton data set, using a couple species from that, a couple algae species, and looking for effects of temperature and phosphate, total phosphate. So within the time series field, what are some of the general approaches that we might use to include covariates? So most of you, I'm sure, are familiar with multivariate linear regression, and you will see that done on time series data. There are problems, and the next slide, I'll kind of point you to things to be aware of. Another common approach is that we use a regression. I put here linear, but you can think more generally that it's just some kind of regression, but our errors in that model are autoregressive. So we're modeling those with an ARMA process. And then lastly, and what we're going to be doing a lot of in this course, is what would fall kind of under what's called the ARMA-X approach. And that is where your covariates are affecting this underlying process. And we're going to be working with the state space version of those models. So you have this hidden process. I'll show you how that's different from this one in a moment. I also want to point out that we use the term MARSS, multivariate autoregressive state space. If you run into the term vector autoregressive, that's the same thing. It would be a vector autoregressive state space model would be the same as a MARSS model. Just different terminology. All right, so I just wanted to include this slide because you do see multivariate linear regression of time series data. You can do that, but you do need to be careful. And this is a really great online book that's written by the author of the forecast package. And they have a chapter on how to do linear regression, a multivariate linear regression with time series data, and the kinds of things that you need to be careful about and when it can be appropriate. In this course, we're not going to do that. We're going to work with actual time series models, but I wanted to put this here because you will see this often. And in your work as a scientist, you're almost certain to review a paper at some point where they have used multivariate linear regression or nonlinear regression, whatever, on time series data.
Hey, Eli.
Yeah.
I will cover this a little bit on Thursday.
Excellent.
So you will get a chance to see that.
Okay. So let's go to the next one. So a linear regression with autocorrelated errors. I'm not going to spend a lot of time on this because I want to jump to the state space models, but I want you to see it again. I covered it a little bit on Tuesday. So that model is something like this down here. So we only have one equation, right? So this isn't a state space model, just have our observation. And a linear regression with autocorrelated errors is going to look like this. You have your observations, and it's got a T there, their time series data. And it's just your straight linear regression equation. You've got your intercept here, and these are your covariates, which are measured at time, your explanatory variables, and that's your effect matrix. So that's your classic multivariate regression equation. And what's different here is that you're not modeling those errors as temporally independent. You are modeling them with some ARMA model here. I've written an AR2, but more generally, it could be have both AR and moving average components. So that means it could have this part, and then again, you model those errors as having some autocorrelation. So it could be a fairly complex autoregressive process. In R, you can fit that with the ARIMA. If you were to use XReg, that's what it's doing. It is doing that linear regression, but it's modeling your errors as an ARMA process. And in the forecast package, you can do this with AutoARIMA nicely, just packs in that XReg. So that's really nice. It's only going to work with univariate data, but it's going to work really well. Here's an example that is from that online textbook. So this is your consumption, and this is your income, and you're trying to model consumption as a function of income. And if you were to do just a regular old linear regression on this, so if I say Y is consumption and my explanatory variable is income, you do a linear regression, you run it into check residuals. Remember, that's a function in the forecast package, but it will work on a lot of different types of models. It's going to print out your basic diagnostics that you're going to do on residuals. You're going to look at them. Okay, and then key thing, you're going to look down here, and you can see that we've got some issues with our residuals if we just did a linear regression. We could use the ARIMA function to find the best linear regression with autocorrelated errors model. And what it finds, I didn't show the output because it's kind of verbose, but what it finds is that this model here is best. So it's modeling the errors with this model. It's just the error term that has that structure. And now when you do check residuals, you see that they look good. You would expect a few of them to be over the blue lines here, but you're really looking down here, and it's gotten rid of that short correlation that we saw in our residuals. All right, so that was a linear regression with autocorrelated errors. I'll show you that equation again. So that's our y here, and this is the autocorrelated part. Now, how does that differ between what's called a ARMA X model? And here I show an AR1 with sort of X, and what that is something like this, where now we have this autoregressive process. X is a function of x at t-1, and now we have covariates here. So these covariates are either explaining or driving this step-to-step change in our autoregressive process. Okay, so let's think of some concrete examples here. So concrete example, what if this were a random walk? So a random walk, I'm going to start here and then I'm going to jump here, and how big that jump is, how far I go, is affected by my covariates here. So say that's temperature. Maybe when it's a really hot temperature, you make a big jump, and when it's cold, you make little jumps, something like that. So now let's go to the state space form. So now we have both the observation and we have the hidden state process. And you can see it kind of looks like we're combining those two ideas, and we are. So I'm writing it here in the univariate example. So I've got a univariate y and a univariate x. Just start simple here. So here we have a covariant that is affecting how that hidden state jumps, moves around from time step to time step. And now we have our observation of that hidden state, that hidden trend, that trend that's going to be this random walk. We're observing that random walk, but our errors in how we observe that random walk are affected by these covariates, or they're being explained by the covariates. Let's see some examples. So here's an example. So what is this model that I'm showing here? This is a random walk with drift, xt minus 1 plus u. That's your random walk with drift. But I've got the covariates here. And I observed that, just a straight observation of that with some independent error, some white noise error. So here's a real world example of that. Say you tagged some animals in the ocean, and you get back your tag data. They're just going along the coastline. It's one-dimensional. Okay, they're just going up and down the coast. And what you want to model, understand, is how water temperature affects their speed. Or maybe you're looking at time of day. Maybe you're curious if there's a time of day when they're particularly active, moving really fast. So in that case, you could include that covariate to water temperature or time of day, something like that, into this and model how that jump length is affected by that covariate. What about if we put that covariate in the y and we didn't have it in the x? So now our hidden state that we're trying to track is just a random walk with drift. But now we observe that random walk and our errors are affected by our covariates. So what's an example of that? So an example is we're tracking population size in a stream year to year. But in this stream, the turbidity in the stream affected our observation error. Oh, I see there's some chats. Did you want to make a comment about that, Mark?
No, I think it's there. I mean, I'll talk about this a little bit on Thursday, but in general, right, you've got a deterministic part on the right-hand side of the equation and a stochastic part. And the combination of the variance and the combination of those two has to equal the variance of the whatever's on the left-hand side of the equation. So as you add in more meaningful covariates, the variance explained by those goes up and your residual errors goes down, 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 down.
Right.
It's the same whether that's on the observation side or the process side.
Right.
And in general, in these types of models, the process errors are things that we didn't measure, we don't know what they are, so it's just residual noise, right, in the system. But yeah, if there was something like air temperature that really was that proximate driver, and we could identify that as such, then adding that in would help to reduce the variance on those errors. And you could, so yeah, the phenomenon that Eli was describing pertains to both of those equations in that state space model.
Yeah, so I guess like the way kind of to think about how these errors are different is that an error in your observation doesn't change where you're gonna like start at the next year. But in the process part, in the random walk part, if I have a really good year, or say, let's take movement, okay, because that's a little easier to understand. So if I jump really far, the next time I jump, I start where I jumped to. So the process made this jump. My movement, my location actually made a jump. If I have the error here, my location error, so the animal's here, but I say it's way over here, so I have a big error. Well, the next jump, the animal's not going to be as if it was over here because it's not actually there. So you don't have, with the observation error, there's not kind of this feedback going on where the size of the error affects where the population is going to start from. That means where it is at time t minus 1 for the next year. And I guess in terms of like how you would use covariates in your model, you know, people use these types of models for so many different types of questions. And it just really depends on your question, whether you have a really good idea of what might be driving the underlying process, and your goal is to understand what's driving that process. And then other cases, it's just, as Mark says, it's just some sort of like, you know, process that you're trying to estimate, but it's these, you know, unknown errors. All right, so now let's go out and move away from the univariate example. So I don't just have one y and one x. I potentially have multiple observations and multiple x. So for example, let's start with a simple one where I have one x. So there's one underlying state. And let's say that's a temperature profile. but I have multiple sites where I'm measuring that temperature. I'm monitoring, say, the temperature in a lake, and I have multiple buoys around in the lake, but I'm treating them, all those buoys, as being an estimate of this kind of overall average lake temperature. So then I have multiple y and one x. And I might want to model using some covariates of what I think is affecting that temperature, and then some totally different covariates of what I think are affecting how well my buoys are measuring the lake temperature. So let's see a really common example of this with movement data. So typically your movement data would be, say, lat long, x, y. So that's fundamentally a multivariate process. Your x is your lat and your lon locations. So you got two time series going on there. And then your observations are the two also. So the x's are where the animal really is, and the y are where you estimate that it is at that time. So both of these are two-dimensional. And in this model, say you're trying to estimate how that animal is moving, the speed of its moving, how that relates to underlying covariates. And I gave an example of this with temperature. I've seen a number of studies doing that. It might be other like variables, food density or something, variety of things that covariates people will include in these movement models. So let's see an example. Now let's kind of break it down. Like when I'm showing here, you should think of these as matrices. I mentioned that they're two-dimensional. Well, let's actually write that in matrix form so you can see what it looks like. So this would be that model where I have my lat and my long, and I'm, say, modeling it as a function of temperature and TP. I don't know why that would make sense, total phosphate. I probably should have used a different covariate for that. But just imagine I have these two covariates, and this is what it looks like. So at time t, I have my measurements of those covariates, and then this is my effect matrix. So that is going, so you can kind of see how it does that matrix multiplication. This temperature at time t is going to be multiplied by that, plus this by that, and that's the effect on the x. And then same thing here, got that value there times here, that value there times there. It's going to be the effect on the x2. So if we look at, say, the x1 and just write that out, it looks like this. So that t minus 1 there and there. So I showed here one structure for this effect matrix, but our effect matrix doesn't have to look like that. We can use that to model all kinds of potential relationships between our covariates and our process. So let's see some examples. So that should be TP here. So in this case, this effect matrix has all the same values. What is that saying? That's saying that the effect of temperature and TP is the same, both across both covariates and also across both the whatever those x rows are measuring. So if that's location, it's like our jump length in the lat long direction and the lat direction. Or say if our x's are different species, it would be that these covariates have the same effect on the different species. This is the one that I showed in the previous slide. So in this example, the covariates have different effects, but those effects are the same across the x's. So same across like lat long jumps, or same across species, same across sites, whatever my x is. Not limited to that though. I could say, oh no, I want all the effects to be different, potentially different. So in this case, the covariates can have different effects, and they can be different across whatever the x's are modeling. Or I could say, nope, the temperature effect is the same across the x's, but the TP effect is different. Or, you know, I could even say, I said these two are the same and those two are different. I don't think I've seen that before, but I guess it depends on what your covariate is. All right, so, okay, question. Would it make sense to also incorporate covariates that might explain the underlying mean of the hidden state? The mean of the... Yes, I'm pausing here because depending how you set up your x equation, it would have the behavior that I think you're imagining. So if I put a term in front of that x here, so I made that autoregressive process stationary, that means that it kind of wiggles around, you know, a level. Well, in that case, this u term is changing the level, and these are going to shift that level up or down. In the short term, it's going to mean a jump. But if that stays at that if that covariate, say the temperature went up a degree and it stayed there for a little bit, the effect of that would be that the level of that underlying x would go up. Also, conversely, if I could also get rid of this x, and then this would just be a deterministic level. Well, it's not a determinant, it's a level with some error. So that would be, you know, a very clear example where it would be affecting the level of the hidden state. And depending on your the context of what you're doing, you might do that. Okay, great questions. Keep them up. That's really good. Let's go into more of the details. Okay, so what about covariates in the observation side? What's going on there? So, so let's say my y equation looks like this. So here are my observations, and they're observing this hidden trend. So that whatever, it's sort of a level, think of it, that hidden level. And then the difference between my observation and that level is here. So it's affected by this covariate. So let's see some examples. So now I have different covariates. I have temperature and wind. You don't have to have the same covariates across your underlying state and your observation. Definitely not. You know, things that affect observation area might well not affect the underlying state. So, like for example, the you know, that example I gave with population growth. Right, so there are things that would affect how you can observe the population that are really going to have no effect on the population size. So definitely you might expect to have different covariates in the different parts of the equation. So let's see what this this looks like. So I've got these two hidden states, and in this example, I have three different observations. My first two observations are observing the first hidden state. So for whatever reason, I have two different sensors or two different syntheses of that hidden state. And then for the last one, I only have one observation. So these two are associated with this one, and this one's associated with this one. And now I have observation errors for all these observations, and I'm modeling them as a function of temperature and wind. And in this case, I'm modeling it as if temperature and wind have the same effect on each of these types of observations. So that temperature and wind, it's not affecting that underlying state. It's just affecting my observation of that underlying state. So then my observation looks like this. Here's the thing I'm trying to measure. And then here are the covariates that are explaining the difference between my observation and that underlying state. Okay, I see I've got some more questions here. Oh, okay, great. Thanks, Mark. Okay. Again, the structure of that D matrix, that effect matrix, can model a variety of different scenarios of how the covariate affects the observation errors. So here's an example where I say, well, I think the covariates affect that site that are both modeling the X1. I think those covariates are going to work or affect the observation errors similarly. But in my third site that's modeling that other X, I think that only temperature is having an effect. Wind is really not a factor there, so I'm going to set that to 0. But the effect of the temperature is totally different than what's going on in those other two sites. All right, so I went over some of this, why we include these covariates in the MARSS models, in these state space models. But I want to pause here. Okay, I see Mark has answered things, but I want to pause for a moment to see if anyone has questions or wants more examples of how you might use these covariates or what they might mean. Okay.
Okay, Eli.
Yep, go ahead.
I just wanted to also mention, because this will inevitably get this question at some point, is what covariates to include in which of those equations? And that is pretty much a system specific question and answer, but it's not, it wouldn't be uncommon or unusual that you might include the same covariate in both of those equations. So for instance, if you were working on lizards and you know that the population dynamics of lizards is probably strongly influenced by temperature because they're cold-blooded. And for those of you who have ever tried to trap lizards, when they don't move around, it's a lot easier to lasso them than when they do. Or if you're using pitfall traps and they're not moving around, then you won't catch any either. So in that case, you can imagine where temperature is affecting the underlying biology, but it's also affecting your ability to observe what's going on. So, but that's where just, being an ecologist for a minute and throwing away the statistician label and really thinking about what it is the system you're working on and what are the things that would affect them either from a biological standpoint or from an observation standpoint. So like Eli's example earlier of turbidity in streams, right, makes it really hard to see what's going on. That turbidity could also do things like smother eggs that might be on the bottom of the stream bed or that sort of thing, right? So it's entirely possible that the same covariate could be affecting two different things going on there.
Yeah.
And can I ask a follow-up?
Yeah, go, please.
Do you ever, if you're including the same covariate for both the process and the observation error, do you ever run into issues with like the model not being able to separate like where that effect is actually occurring, or like partitioning the variance between those two errors?
Yes, definitely. Especially if the if your X model here, if it didn't look like a random walk, but it had some mean reversion, so it had a term here, a B term here, then that can be a big issue. And I will say that, you know, this question about, well, first off, what is the right structure of the model to use? That is often the research question. The first research question is like, you're doing some type of model selection exercise. How you choose to do that model selection can definitely vary, but you are doing some model selection to try to determine how to structure your model, where to include those covariates, how many states are you using, hidden states are you using in your model. You're going to see examples of that on Thursday when Mark's going to start to go into that. And we're going to start to, as we go forward, you're going to start to be using model selection to help you decide on a model structure or how much weight to put on different model structures. And this question of where to put the covariates is one of those questions. In the lab, I walked through in chapter 8, I kind of walked through an example of studying this with the Lake Washington plankton. It's a problematic example because it's not clear cut. All right, when you show things to students, what you would like to show is like, oh wow, and it was completely obvious where to put the covariates. And this is an example where it's not obvious, and where you'd have to, like, you know, we'd be getting at the whiteboard a lot and saying, okay, why is this not working out? What are we not understanding about this? So I'll probably change, I'm planning to change this chapter so it's a little more clear cut, but it's probably more realistic right now. But I would definitely look at that and kind of looks at, it shows you how, you know, you're using, in this case, AICC to weight how well these different models are explaining the variation in the data. In these first part of the course, we're using AICC a lot. It's really easy to use. It's going to be easy for us to make these, you know, comparison tables across models. You will be introduced to other approaches for doing model selection later in the course. I don't want you to give the impression that's the only way that you would do model selection. Okay. Yes, any general wisdom about number of covariates that you might include? Is having too many a consideration? Absolutely, it's a consideration. You include too many and you're just going to overfit your data. So I guess I would say the biggest piece of wisdom is that do not include collinear covariates in your model. You are creating huge statistical problems that you will suffer greatly with. And there are approaches for dealing with that. And I, on the, let me go here. I put a link to a chapter on that that's going to go all into the nitty gritty of doing, like, you know, penalized regression and trying to figure out how do I, you know, select my covariates where I've got collinearity. And it's, yeah, it's right here, this chapter 6. So if you're thinking about that, I mean, you can skim that. It's going to show you an example with fisheries data. It's a difficult problem. And I I would say, to the extent you can, don't include collinear covariates. So that's the big piece of advice. And then in terms of how many covariates to include, how do you assess when you've included so many that you've overfit your data? Personally, the approach I take is using cross-validation, which Eric Ward is going to talk about. I've found that that's kind of the easiest way for me to detect whether I have that problem. All right, so let's take a few minutes. I think if we can do it in like 15 minutes, that'll be great. And go through an example. So we'll do the breakout rooms, and you will go through this code right here. And it's got 3 questions for you to think about of how you would change your D matrix to answer a few questions. So let me open up that before we jump to it. Okay. So seasonality. We've seen an example with this data that we just worked with. It's got a regular cycle in it, a regular, in this case, annual cycle. Here's an example with our Washington Chinook landings. Again, these are salmon. They have a strong seasonal cycle in the data. So how do we deal with that seasonal cycle? So we're going to include a covariate to explain that, a separate covariate. And I'm going to talk about 3 different approaches that we could use: factors, polynomials, and sines and cosines. So with a factor approach, we are basically going to be estimating a coefficient, a level, for each month separately. I'm going to talk about monthly data here. If you had quarterly data or hourly data, you're just changing the period of the data. But I'm going to be talking about monthly data. So if I'm going to do treat the month as a factor and estimate an average January effect, an average February effect, what I'm going to do is I'm going to include this covariate where I'm including 12 of them, a January covariate, a February covariate, etc. And at time t, if I'm in January, the January covariate is going to be 1. And if I'm not in a January, it's going to be 0. If I'm in February, the February covariate is going to be 1, and it's going to be 0 otherwise. So that covariate, there are going to be 12 of them. It's going to be a column that's going to be all 0 except a 1 in the row for the month. So the math looks like this. And if you were to dig into, say, the LM function in R, when you were, if you include a month as a factor, you're going to run into a matrix that looks like this. That's what's happening under the hood there, and you can make that happen in all kinds of models. So your covariate matrix is going to look like this. It's going to have this diagonal of 1s in it. And you're going to have 12 rows, and the number of columns is however long your data set is. And then you have a 1, so it's got sort of 1, 1, 1, 1, 1 diagonal, and then it's going to start over again. Back when you get back to the January all the way down to December, and then it's going to start over again. So for your 12 months, going to have a chunk there, and it's going to have a diagonal with a 1, and then the next year, same thing for your covariate. So that's how you set that up. And then your covariate matrix is now going to have 12 columns, 1 for each month. So for the Chinook example, it would look kind of like this. So I got that. And this would be a model where I said those monthly averages were the same for Washington and Oregon. You can see it has the same values in the top row and the bottom row. All I'd have to do to make different monthly effects is change the values. So make this not equal to that, have this be, you know, D or something. Okay, great. The chapter on covariates in the manual, I think that's chapter 8, I believe. It shows an example of how you could create that matrix. Here's another example. It's pretty tedious, I admit, but there's a number of different ways you can create that. You just want to make, for each time step, you're going to have something that looks like this. You're going to have 12, one for each month, and then a 1 if it's a January, a 2 if it's a February. So this is January, February, March, April, May, June. And the key thing to note here is when you get to the I'm at December. Once I go to 13, it's back in January, so it's going to have a 1 back up there again. And this is what your matrix would look like if the effects are different. So you can see this is January for the first row, January for the second row. The key thing is they're just different. And if you want to model them the same, make them the same. And also note here that if you took this approach and say you wanted to have a summer effect and a winter effect, there would be nothing to stop you from saying, okay, I want all of these to say summer and all of these to say winter. That's a choice that you make. And again, you'll do a model, it's part of the model selection process, model evaluation process early on to decide what structure that you want. All right, so that's 12 parameters we're estimating for each Chinook series. So that's 24. Imagine if we had 5 states. Oh my goodness, we're getting up to 60 different, 5 times 12. Goodness, we're estimating a lot of parameters. That's probably going to run into trouble. So maybe we don't want to do that. So another approach is to use a polynomial. And here I'm going to show a third order polynomial. And the way that works is that I introduce these covariates that are the month, which is 1 to 12, month squared, and month cubed. And so now the covariate effect is going to be the this polynomial right there. And that's going to work real well to model a lot of pretty generic seasonal effects. So the equation now looks like this. Again, you've got this covariate matrix, and you're going to have one column for each time step, but now it's going to be the month. So January is 1, 1, 1 squared, 1 cubed. February is 2, 2, 2 squared, 2 cubed. So it's just like that. And this last one is 12, because in this instance, in our Chinook example, it ends with December. If it ended with June, there would be a 6 in this last column, but this data set happens to end with December. And now my month effects matrix is quite a bit smaller. Oh, this is much better. Now I am estimating at most 6 parameters. In this case, I'm only estimating 3 because I said the top and the bottom are the same. But if I said they were different, I'd be estimating 6. So that's much better. Okay, so that's just showing you some code, what that looks like. And this is the example showing you what that matrix looks like if the effects are different. And this would be the effects across the Washington and the Oregon Chinook are the same. And the last one I want to show you is using sines and cosines. So in this case, I introduced two covariates, and the covariates are the sine, the t. T would be 1 to the number of time steps. So like if you have 100 time steps, t is 1 to 100, and p is the frequency or the period. So for monthly data, that's 12. Quarterly data, that'd be 4. And then then you have the cosine. The equation, hopefully, oh, that's what it looks like if you plotted those covariates. And then this hopefully is starting to look familiar. So each one of these is your your first time step, second time step, and you just have these sines and cosines. And now, oh, fantastic. I'm just estimating at most 4 parameters for my Washington and my Oregon. That's much better. Creating that covariate is quite simple. You're just taking the 1 to the length of your time series. So I don't know what it was for the Chinook, but say it was 100 time steps. So it'd be 1 to 100 divided by 12. And then I add to that a row for the cosine. So it's really easy to make this covariate, much easier than the monthly factors. If you go to section 8.6 in the lab manual, it's going to show you an example of using all 3 methods to analyze seasonality in the Lake Washington plankton. And there you can see how this is really powerful at a way to estimate what the seasonality is in a large data set. So in this one, you can see that there are some definite differences in the seasonality in these 3 species within that plankton data set. So it's using the same data set you were playing with, but now we're looking at the seasonality and estimating that seasonality. So what you see here is this is the effect and this is the month. So for most of them, the peak is in June, July. And in this one, the diatoms, it's quite a bit earlier. So it's very different. And another cool thing about using the sines and cosines, I'm going to try to write up an example for you, is that you can model changing seasonality really nicely with these. On Tuesday, Mark's going to talk about dynamic linear models where we model time varying effect sizes. So right now, those effect of the covariates have been constant, but we could allow those to evolve with time. And Mark's going to talk about that on Tuesday. And you can use these sines and cosines very easily to model how seasonality might be changing in a population using that, using what you'll learn on Tuesday. All right, I am going to stop there.